Hello everyone. In this session, we'll discuss about timers in PIC16f877a microcontroller. Okay. So before going to discuss the timers which are present inside this controller, let us see what is a timer first. So timer is basically a peripheral, or we can also call it as a register, and whose application is or else it can be used as a counter for counting internal or external pulses. Okay, so if it is an up counter, then it starts counting from 0 value and reaches its maximum value, and if it is a down counter, then it starts counting from its maximum value and reaches its minimum value. Okay, now in case of this PIC, we have up counters, so they'll start counting from its maximum value. Okay, and as soon as they reaches their maximum value, so they'll start counting from minimum value, that is 0, and as soon as they reaches their maximum value, okay, so from then if any event occurs, then a rollover condition takes place. So here rollover is nothing but a transition from its maximum value to its minimum value. Okay, so if you can take an example of 8-bit, now its minimum value would be 0 and its maximum value would be 255. Okay, so after 255, then it again rolls over to its minimum value. Okay, and this particular event is nothing but rollover condition or overflow condition. Okay, so whenever this particular condition is generated, then it will generate an interrupt. Okay, so let us see what are the timers and how we can use these timer peripherals in PIC microcontroller. Okay, so here we can use these timers in two modes. One is counter mode and the other one is timer mode. So basically counter is used for counting the external events, and timer is used for providing or generating some delay. Okay, but what happens internally in these two modes? Counter will count the external pulses given through some counter pins, and timer will count the internal pulses. It means whatever the processor or whatever the clock which we are giving to the processor, those pulses are counted by this timer. Okay, so this is what counter counts the external pulses and timer counts the internal pulses. So there are three timers inside a PIC16f877a. Okay, as you can see, Timer0, Timer1 and Timer2, and you have one more variant, that is virtual timer. Okay, so here two of these timers are 8-bit timers, and the Timer1 is a 16-bit timer, and all of these timers are provided with Prescalar. Okay, and along with this Prescalar, a Postscale is also provided for this Timer2. So we'll discuss about this Prescale and Postscale when we come across these timers. Okay, now let us see the features of Timer0. So it's an 8-bit timer counter. I can use it as timer or else as counter with Prescalar or without Prescalar. Okay, and it is readable and writable by using some software instructions. Okay, and internal or external clock set. It means I can give the clock to internal source or else through external source. So if I'm giving to internal source, then it is considered as a timer for generating some delay. Okay, and if I'm giving the clock from external source, that is through some counter pins, then it is considered as a counter operation for counting the external pulses. Okay, and it will also generate an interrupt whenever it overflows from its maximum value to its minimum value. So it is an 8-bit timer, so its maximum value would be FF. Okay, and edge select for external clock, so we can also select the type of edge for counting the events. Okay, so what is this Prescalar? So Prescalar is a block which is present inside this timer module, and it will divide the incoming clock by a number. Okay, now that number is decided with the help of this option register. Okay, so with the help of Prescalar, we can divide the incoming clock by some factor. Okay, now that factor is decided with the help of this option register. Okay, so here you can see, now this is the clock frequency. Okay, and it is getting divided by so many factors like 2, 4, 8, 16, 32 and so on up to 256. Okay, now all of these divided clocks are given as an input to this multiplexer. Okay, now the output of the multiplexer depends on these particular bits, PS2, PS1 and then PS0. These are called as Prescale select inputs. Okay, now these bits are present inside the option register. So by programming these registers, I can select any one of these clocks as an input or as an output of this multiplexer. Okay, so let us see how to program these bits and how to select any one of these clocks. So these are the registers which I need to program when I'm using Timer0. Okay, option register, Timer0 register, and then INT, that is interrupt control register. Okay, so let us start with the option register. Now we'll start with bit 7, which is our MSB. So RBPU whole bar. Now this indicates it's an active low bit. Okay, so if a 0 is written into this particular bit, then the pull-up gets activated for port B pins. Okay, if you are programming this particular bit with logic 1, then pull-ups are disabled for port B. Okay, in the same way, you have one more bit, that is interrupt edge. So with the help of this particular bit, you can select a particular edge for generating an interrupt. Okay, so if you want to generate an interrupt, so we have an external interrupt pin which is provided for RB0. Okay, now if you are programming it to 1, then it means a logic high or a rising edge on RB0 will generate an interrupt. Okay, and if you program it with 0, then a logic 0 or a falling edge on RB0 pin will generate an interrupt. Okay, now apart from these two, there are some bits now which these are related to this timers. Okay, so T0CS Timer0 clock source. Okay, so you can select the clock source for this timer peripheral either from external source or else from the internal clock. So if you are selecting it from the external source, we call it as counter. Okay, if you are selecting it from the internal source, then we call it as timer. Okay, now if you are programming this bit to logic 1, then a transition on T0 CKI pin. So it means, so by programming this particular bit to logic 1, it means that now this timer is acting as counter. Okay, this peripheral is now acting as counter. Okay, it will count the external clock pulses which are given through T0 CKI, which is nothing but Timer0 clock input pin. Okay, so whatever the clock pulses which are coming from this particular pin, now those pulses are counted by this timer. Okay, and if you are programming this bit to 0, then internal clock source or internal clock pulses are given to this timer, which will count those internal pulses. Okay, now with the help of this particular bit, that is T0SE, okay, select edge. We can select a particular edge for counting the events. Okay, that is high to low. So if you are programming it to 1, it means a falling edge on this T0 CKI will increment the counter. Okay, if you are programming it to 0, then a rising edge on this T0 CKI will increment the counter. Okay, and then we have a prescale assignment. Okay, as we know that there is one prescalar block. Now this prescalar block is shared by two modules. One is Timer0 and the other one is watchdog timer. Okay, so we have only one prescalar module in between Timer0 and the watchdog timer. Okay, so both of these modules are going to share this particular block. Okay, now if one of the module is using prescalar, then the other module cannot use the prescalar. Okay, so let us see. So if this particular bit is programmed to 1, then it means that now this prescalar is assigned to watchdog timer. So watchdog timer can only use prescalar. Okay, if it is programmed to 0, then it means that now this prescalar is assigned to Timer0. Okay, now Timer0 can only use this prescalar block. So by default, Timer0 will be using this prescalar block. Okay, now as we have discussed some selection inputs like PS2, PS1 and PS0, these are prescale rate select bits. Okay, now if this prescalar is assigned to Timer0, now if you are programming these 3 bits to 0, 0, 0, then it means now Timer0 gets incremented by 1 for every 2 clock cycles. Okay, then if you are programming it to 0, 0, 1, then it means Timer0 gets incremented by 1 for every 4 clock cycles. Okay, in the same way for 8 clock cycles, 16 clock cycles, 32 clock cycles. So in the same way for the last combination, that is 111. So for every 256 cycles, timer gets incremented by 1. Okay, now if you are assigning this prescalar to watchdog timer, then it will have its own ratios. Like if it is programmed to 0, 0, 0, then for every single clock pulse or for every single clock cycle, this watchdog timer gets incremented by 1. So this is how we are going to program this option register. Okay, so here this RBPU is related to pull up of port B, and this is a interrupt edge select. And if you want to use timer, or if you want to use this Timer0 peripheral as timer or else as counter, then you have to program this T0CS. Okay, if it is programmed to 1, it means it is acting as counter. If it is programmed to 0, it means then it is acting as timer. Okay, and then we have select edge. So you can select a particular edge where the counter gets incremented by 1. Either it might be rising edge or else it might be falling edge. Okay, and then prescale assignment. By this you can assign the prescaler block to any one of the module, that is Timer0 or else words of timer. And then you have prescale bits, by which you can select the ratio of incrementing the Timer0 register. Okay, now we have one more register, that is Timer0. Now this is the register which is going to hold the count value. Okay, whether it is used as counter or whether it is used as timer, now this register is going to hold the count value. Okay, so if this peripheral is now used as counter, now this register holds the count value of the external clock pulses. If we are using this peripheral as timer, then it will hold the count value of the internal clock pulses. Okay, now it's an 8-bit register. So whenever it overflows from FF, that is its maximum value, so whenever it overflows or rolls over from its maximum value to minimum value, then it will generate an interrupt. Okay, now we have one more register, that is INT con register. Now interrupt control register. Okay, so GIE is nothing but global interrupt enable and PIE is nothing but peripheral interrupt enable bit. Okay, so these two bits should be programmed to 1 whenever we want to generate an interrupt. So what is the difference between interrupt enable and interrupt flag? So for every interrupt we have two flags. One is interrupt enable bit and the other one is interrupt flag bit. Okay, so if interrupt enable bit is activated, okay, then the processor will execute the ISR whenever an interrupt is generated. Okay, if interrupt enable bit is deactivated, then the processor will not execute the ISR even though the interrupt is generated. Okay, then what about interrupt flag? Interrupt flag will give you the status of the interrupt, whether it is generated or not. Okay, so for every interrupt you'll have two flags. One is interrupt enable and the other one is interrupt flag. Okay, so here if I want to generate any kind of interrupt, it might be peripheral interrupt or it might be software interrupt, then this GIE should be enabled. So it should be programmed to logic 1. And if you want to generate any peripheral interrupt, then this particular bit should be programmed to logic 1. So as I said, for every interrupt, so Timer0 will generate an overflow interrupt. Okay, so for that interrupt you will have an interrupt enable bit as well as interrupt flag bit. Okay, now here you can see one IE bit. IE indicates Timer0. Now here Timer0 IE indicates interrupt enable, and then Timer0 IF. Now this indicates interrupt flag. Now this flag will give you the status of the interrupt, and this flag, if you program or if you enable it, then the processor will execute the ISR related to this Timer0. Okay, so if you're programming it to 1, then the processor will execute the ISR of Timer0 when Timer0 interrupt is generated. If you're programming it to 0, then processor will not execute the ISR even though the Timer0 interrupt is generated. Okay, and if you see this Timer0 IF, so whenever overflow interrupt is generated, then this particular bit will become 1, indicating that Timer0 interrupt have been generated. Okay, and then you have INTE. So if you are enabling this particular bit, then this RB0 pin will be acting as a interrupt pin. Okay, if you are programming it to 1, then RB0 will be acting as an external interrupt pin. If you are programming it to 0, then the RB0 will be acting as the general GPIO pin. Okay, so next you have interrupt flag. Now this will give you the status of this RB0 pin. Whenever an interrupt is generated, then this flag will become 1, indicating that external interrupt is generated. Okay, and then you have RBIE and RBIF. Now these two are related to interrupt on change feature of port B. Okay, so we have one feature for this port B, that is port B will generate a special interrupt whenever a change occurs on the port B. Okay, so if you are enabling this particular bit, then it will generate an interrupt. Okay, and this will give you the status of that particular interrupt on change status. So with the help of these three registers, or by programming these three registers, we can use Timer0 effectively. Now let us see the operation of this Timer0. As you can see, T0SE, which is used for selecting a particular edge, either rising or falling edge. Okay, for the T0 CKI, which is nothing but timer or counter pin. through which you are going to give the clock pulses. Okay, and you have a multiplexer. So with the help of this TO0, that is T0CS, you can select one particular source. You can select one particular clock source. Either it might be external clock source, or else it might be internal clock source. External is T0CKI and internal is your oscillator clock. Okay, so any one of the clocks is selected. Now that clock is given to one more multiplexer, which is whose selection bit is PSA, which is nothing but Prescalar assignment. Okay, now if you are programming this particular bit to logic 1, if you are programming it to logic 1, now let us see what happens. Now this is given to here. Okay, now assuming that PSA is 1, so as it is 1, now this particular clock, so PSA, if PSA is 1, it means that watchdog timer is now using Prescalar. Okay, so it means the clock which is coming out of this watchdog timer will be given as a prescale input. Okay, and one of the output is selected by using this PS2 to PS0, and now that output will be given to the watchdog timeout. Okay, if you are programming it to 0, then Prescalar is assigned now to timer, and the output of this is given here. Okay, so as it is 0, now this 0 input will be given to synchronous 2 cycles, which will synchronize the incoming clock with the already oscillator clock, and then that output clock is given to timer 0 register. Okay, so this is how the operation takes place of this timer 0. Okay, now let us see timer 1. So timer 1 will start with features. As you can see here, it is a 16-bit timer or counter with Prescalar. It is readable and writable by using instructions or by using some software instructions, and programmable Prescalar of 1 to 48. Okay, in case of timer 0, you have a programmable Prescalar of 2, 4, 8, 16, 32. Okay, but here you have only 4 options or 4 factors, that is 1, 2, 4 and 8. Okay, internal or external clock select. So we can select the clock either internal or else external, and external clock can be synchronized or asynchronized. Okay, and then interrupt on overflow, it will also generate an interrupt whenever overflow condition is reached, and second crystal is permitted. It means I can connect a separate oscillator for this timer 1. Okay, so let us see. So if I want to use this timer 1, then I have to access these registers, that is timer 1 low and timer 1 high, timer 1 control register, PIR1 and then PIE1. Okay, let us see how to use this. So timer 1 low and timer 1 high, these are the two 8-bit registers. Combinedly they become 16-bit register. Now these registers will be holding the count value. Okay, as similar to TMR0. Okay, now as these are as it is a 16-bit register, now its maximum value would be 4F. So whenever it rolls over from 4F to 4 zeros, then it will generate an interrupt. Okay, now let us see timer 1 control register. Will start from these bits. Okay, so here these bits indicate reserved bits. Okay, and T1, CK, PS1, PS0. Now these are prescale bits. Okay, so if you are programming these two bits with 0, 0, it means this timer 1 low and timer 1 high gets incremented by 1. Okay, for every one single clock cycle. Okay, and if you are programming with 0, 1, then for every 2 cycles this timer register gets incremented by 1. So for every 4 cycles, timer register gets incremented by 1 for this condition or for this combination, and for 1-1 combination, timer register gets incremented by 1 for every 8 clock cycles. Okay, and then you have T1 oscillator enable. Okay, so with the help of this, you can enable or disable the external oscillator. Okay, as I told you that we can connect a separate crystal for this timer 1, so you can enable or disable that particular separate crystal oscillator with the help of this bit. Okay, and this external crystal is only used in case of counter operation, but not in case of timer operation, because timer always receives the clock from the internal source. Okay, and then T1 synchronize. So this is used only when timer 1 is used as a counter. If you are using timer 1 as counter, then you can synchronize the external signal or external pulse with the internal oscillator frequency. Okay, so as you can see here, when timer 1 CS is 1, it means now it is acting as counter. Then you can synchronize, or else you cannot synchronize. Okay, and then timer 1 CS. Now with the help of this, you can select whether this peripheral to act as counter or else to act as timer. If it is acting as counter, then it will get the clock signal either from T1 CKI, that is timer 1 clock input, or else from the external oscillator, that is crystal oscillator T1 oscillator. Okay, so if you're programming this timer 1 CS to 1, then this peripheral would be acting as counter, and it can receive the clock signal either from T1 CKI or else from timer 1 oscillator, that is separate crystal oscillator. Okay, so it will receive from the separate crystal oscillator only when this oscillator bit is enabled. If this is disabled, then it will receive the clock from the T1 CKI. Okay, and if this bit is programmed to 0, then it will get the clock from the internal source that gets divided by 4, and now that frequency will be given as an input to this peripheral. Okay, and then you have timer 1 on. So if you program it to 1, then the timer 1 gets enabled. If you program it to 0, then the timer stops. It will not count the pulses. Okay. Now we have a PIR1 and then PIE1. Okay. So peripheral interrupt register and then peripheral interrupt enable register. Okay. Now here you have so many bits like PSP, IF, AD, IF, but out of these bits, for now we'll discuss only the bits which are related to timer 1. Now if you can see here, as I've already told you that every interrupt will have an interrupt enable bit as well as interrupt flag bit. Okay. Now here we have timer 1 interrupt. Now that gets generated only when overflow is reached. That means when there is a transition from maximum to minimum value, then overflow interrupt will be generated. Okay. Now here this is timer 1 interrupt flag and this is timer 1 interrupt enable flag. Okay. Now if you are programming this enable flag to 1, so whenever an interrupt is generated, processor will execute the ISR related to this timer 1. Okay. If you are disabling it, then even if timer 1 interrupt is generated, processor will not execute the ISR of timer 1. And then you have timer 1 interrupt flag. Now this will give you a status of this particular overflow interrupt of timer 1. So if overflow is generated, then this will become 1. This particular bit will become 1. Okay. Now let us see the timer 1 operation here. Okay. Now as you can see, timer 1 clock source. Okay. So with the help of this bit, you can select the clock source. If you're programming it to 0, then it means the internal clock will be given as a input to the timer peripheral. Okay. If you're programming it to 1, then it will get the clock source from the external source. Okay. Now that external source can be T1 CKI pin or else it can be a crystal oscillator. Okay. So it can be a crystal oscillator when this T1 OSC bit is logic 1. If it is enabled, then it will get the clock source from the crystal oscillator. If it is disabled, then it will directly get the clock source from this T1 CKI pin. Okay. And here you have a Prescalar bit by which you can divide the incoming clock by any of one of these factors. Now that can be synchronized, or else we can also synchronize it, or else we can also go with the direct, that is do not synchronization option. So that is selected with the help of this T1 synchronous bar. If this particular bit is logic 1, then it will not be synchronized. External clock will not be synchronized with the internal oscillator clock. If it is 0, then it gets synchronized and then that is given to this AND gate. Now the other input of this AND gate is timer 1 on bit. So if you program it to 1, then the same clock will be given to this timer 1 register. If you are programming it to 0, then the output of this AND gate will always be 0. Therefore this timer 1 will not count the pulses. Okay. So this is how the timer 1 works. Now let us see timer 2 register. So if you want to use this timer 2 peripheral, then we have to access these registers like timer 2, T2 con, PIR1, PIE1, and then one extra register, that is PR2. Okay, let us see what are these registers. So timer 2 is the register which is similar to TMR0 and then TMR1L and TMR1H. So this register will be holding the count value in case of timer or else in case of counter. Okay. Now it is an 8-bit register and this register is always compared with this PR2 register. Just now we have seen one register with the name PR2. So always the value of this timer 2 is compared with this PR2 register. So when both are equal, when timer 2 and PR2 are equal, then it will generate an interrupt as well as TMR2 is reset. Okay. Take an example that now PR2 is holding a value 0x0A. So initially timer 2 register is 0x00. Now 0 is compared with A, as both are not equal, so timer 2 gets incremented by 1. Now it reaches 1. So it gets incremented by 1 until it reaches 0x0A. So as soon as this becomes 0x0a. Now what happens? Timer 2 is equals to PR2, therefore it will generate an interrupt. We call it as now overflow interrupt, okay, and it will reset the timer 2 register, okay. Now timer 2 control register. So in order to control this timer 2 peripheral, you have to program this control register, okay. So we'll come from the MSB bits. So here you have PS3, PS2, PS1 and then PS0, okay. These are post scale bits, okay. So until we have seen pre-scale bits, but what is this post scale? Now if you want to generate or if you want to provide some delay in generating the overflow interrupt, okay, if you want to provide some delay for generating the overflow interrupt, then we have to use this post scale bits, okay. Pre-scale for dividing the incoming clock by some factor, and post scale for providing some delay for generating the overflow interrupt, okay. So if you are programming these 4 bits to 0000, then it means after overflow, okay, so after overflow it will receive one clock pulse and then generate an interrupt, okay. If you are programming it to 0001, after overflow it will stay for 2 clock cycles and then it will generate an interrupt, okay. If you are programming it to the next combination, then after overflow it will stay for 3 clock cycles and then generate an interrupt, okay. And then we have timer 2 on bit. This is for enabling or disabling or on and off of this timer. And then you have prescale bits, like if you are going with 00, so prescalar is 1. It means for every single clock cycle it gets incremented by 1. So if it is 01, so for every 4 clock cycles it gets incremented by 1. And if it is 1x, so it means you can go with 10 or 11 combination, then it gets incremented by 1 for every 16 clock pulses. So similar again, PIR1 and then PIE1. Now these registers will be holding the interrupt enable bit as well as the flag bit of timer 2. Okay. So as you can see, timer 2 interrupt flag and timer 2 interrupt enable. Okay. Programming it to 1 will enable the interrupt. It means processor will execute the ISR when an interrupt is generated. That is timer 2 interrupt. So when this timer 2 interrupt is generated, then PR2 equals, or when timer 2 equals PR2 value. Okay. And the interrupt flag, this will give you the status of the interrupt. So as I told you that it is a period register. Now it's an 8-bit register. Always this register is compared with timer 2 register. Okay. So let us see the operation of this timer 2. Now it can get the clock from the external source, that is F oscillator divided by 4. Now this can be given to the prescaler. So prescaler, as we know that it divides the incoming clock frequency by some factor. It might be 1, 4 or 16. Okay. Now this is given to timer 2 register. It will count the incoming clock pulses. Now as it is counting the incoming clock pulses, now the value present in this register is always compared with PR2 register. If both are equal, that is the output of comparator, then it will reset the timer 2 register, and now this equal output is given as an input to the postscalar. Okay. Here, as you can see here, it is not generating an interrupt immediately as on when the timer 2 equals PR2. Okay, but it is depending on this postscalar block. Okay, so when you are programming these bits to any of the values, then it will generate some delay for generating this particular interrupt. Okay,